Hey, and welcome back to our crafting a crawler series. Um, we got a bunch done in our last one. It felt like a bunch of progress, but at the start of a project, that tends to be the way, right? You get a lot done quickly, and then as you start to sort of tidy it up a bit and make it good, expand it, then things slow down a little bit. But no, I think from the last stream, we effectively we got a window open. We got some tiles drawing on that as a map. We got some movement going. The movement had a bug in the diagonal, in that we move faster diagonally than we do in the other directions. But yeah, the stream of rain was preventing me from fixing that last stream, but today we can hopefully get that done, and we can tidy up some of this, and hopefully we can look at some animation. We can look at some animation and see how we're going to get that into our game in the future. And hopefully we can tidy up a bit of what we did last time, because I said it's there, but it's mostly messy, it's raw, it's all mixed together. There's no sort of separation between the pieces, and that would be nice to have. So yeah, with that gone, oh, we have Captain Crumbs in the chat. Hi, Crumbs. So first up, we should probably look at a spot of animation, because we don't just want sort of static sprites on our screen. So bear with me one sec while I try and remember where I left my files. Here we go. So yeah, if we had this pretty sort of terrible little sprite here for a slime. So I think what we're going to do this time is we'll probably try and give it like a little two frame animation. That'll just sort of we can get the gist of how that works. How that works going. So I think start with, we double the size of the screen, of the image, and then if we drop a guide in here, we can split this. Oh, wow! I was aiming for 32 pixels, and I was dead on there. That's I was expecting a little bit of jiggery pokery there to get it into the right spot, but more accuracy than I thought. Okay, yeah, so that's now the center. Oh, and yeah, I split this and I made it a bit narrower last time, didn't I? But what we can do is if we group those together, which is there, then we rasterize it. It will turn these into single images. There we go. So we've now got two of them, and what I'm thinking I will do is probably for our crude little rendition here, we will flip this over, transform. There we go. We'll flip it horizontally, and where's our pixel tool? There it is. We are going to want some colors. So if we take that one, we can take out this. Oh no, we can take out this the shine on this side, and we can put it back down the other side here. Oh. There we go. And now it will look sort of, I think this will sort of give us a little impression that it's moving. No worry, Crumbs. well, it's nice to have you watching anyway, in and out or otherwise. But yeah, the idea of these streams to me is that I was going to do this anyway, but I thought it'd be fun to sort of share and bring some folk on the journey with me, and hopefully I can get some good ideas off of people as well when it comes to when we start to actually think about the mechanics of the game, and yeah, like. Hopefully we can get some good ideas going and make the game a bit better than it would have been otherwise. We don't need that. Let's minimize that. Yeah, there we go. So we've got an image now. It's got two sprites in it instead of two pictures in it instead of one, and each one is in sort of a 32 pixel by 32 pixel square. So we've got one there and one there, and these are going to be the frames of our animation. So what we'll do is we'll animate between one and another, and we'll put some delay between that, and each time we update the screen we'll sort of look at what the delay is and we'll decide which one we're going to show. So if we export this out, export into the code and assets, images, and we have the slime. So we'll replace that. We'll save this one. And now if we come back here and we look at our slime, we've got the two images there instead of the one. So if we just take it as this, we go back and we run our game and we look at the game window. So okay, so we've got the two images there, which is not quite what we wanted. But it shows we're picking it up fine. Oh, sorry, it was me, not the slime. So when we look at our slimes here, we set a frame. Oh, sorry, we've still got the other window up. So when we look at the code we've got for our slimes, we'll set a frame. We'll set that for both of them, and then we will have a frame duration. Let's say that half a second. Let's see how that looks first, and then we can play with these later and get a good feel for what the delay should be. I actually also managed to get the config working, which we were struggling with at the start of the last stream as well. So so if I look at our config now. This line here is the magic that we needed, and that means that when we sort of hover over any of the sort of functions and things in our editor, we can see the sort of help text and the definition of how it works. And the other thing I sort of decided is normally I use Copilot when I am working on stuff, and it speeds me up, but I feel like when I I normally use Copilot when I'm writing Python or JavaScript, which are the two languages I most work in. And when it completes stuff, I'm like, I know those well like the back of my hand now, those two languages, and I know what I'm looking to do in them. And when it offers me a completion, I can normally look at it and in a split second decide whether or not that is actually what I was going to write or not. And then I know whether or not I want to tab out to get the whole thing completed, or I want to just ignore it and carry on. Whereas with the Lua stuff, I'm still learning this a bit, so until we get a bit more confident in our Lewis skills, we're going to turn off the we are going to turn off the robots, and we'll crank things out by hand. Oh, hi Splash, welcome in. But yeah, so those are a couple of things that I sort of reflected on a bit after the last stream, and that I decided I was going to mix up a bit. Okay, so we've got our spline object, and we've given it a frame and a duration. So now we need to tell it how to draw things, and so we have this existing sprite here, and let's go. Let's go animated instead, and we'll keep that the sprite as well. What is this? Oh, yeah. And this is why we have linters and things in our code. Linters are things that sort of look at the code and tell us where it smells a bit funny and where we could do better. So what it's telling us is that these functions are in Lua. Anything you declare, unless you tell it that it is a, unless you tell it that it's a local. Yeah, let's do these as well. So it gives us a little critique of our code as we're going, and this has so what it's telling us is when we define these, it was defining them in the global space, which means that it would overwrite anything, it would be available anywhere else in the code, and that, although that sounds kind of useful, it tends to not be what we're after. These ones here, we sort of want it as global to some extent, but we'll did we want these? No, because we add these into the objects array, don't we? So we don't actually need a reference to these after they're there. We just need to be able to update them, and we need to know that we can call the functions on them to make sure that they're updated. So yeah, we've got our objects that are being painted, we've got our map, and we've got our tiles. And actually, I think the tile set we probably want as well. So if I do, what I can probably do is declare the tiles. Tile set. Okay, that's fine. That's just offset because it's got a. And we'll set that to nothing to begin with. So that's got a value of nil or nothing. And these we will make local, which local, not low-vol. So these are now hidden away a bit. That is being loaded elsewhere. We will define these as local as well, and we don't actually need the height, so we'll use this special name for a variable, an underscore, and in most languages it's a sort of just a convention there. It doesn't actually mean anything, but if you have a function, a variable that's just named underscore, then generally that means that is a way of saying I don't really care about the value. This wants the. Actually no. We can take the width and the height there, and what this is complaining about is it doesn't like this variation of it. So we'll give it the width and the height, which is what the docs. I think the docs we have loaded are slightly behind what is actually available, but we can use the slightly older form, which is also still supported, where we pass in the width and the height of the image rather than passing the image itself, and then that will then call this get dimensions. Which okay, so we're drawing the quads for our image there. Maybe we want a, as part of this, we want to go local is equal to here. So we'll load our image once, because at the moment we're loading it from disk twice, which means we're using the memory it takes to load that image 2 times over, which, to be honest, it's a tiny image and it doesn't really matter in the context of what we're doing at the moment, where we're still sort of early days and we're not sorry, we're not trying to make everything super fast and efficient right this second, but we can clean up a little bit after ourselves, and that will be a bit better. And then for this, we will also we can also take our we'll take the width and height of our new sprite image, and we'll divide that into chunks, and we'll also have a local for a table. So we'll create an empty table there, and for each of our for each of the each 32 pixel wide chunk of that image, we'll take we'll make one of these quads, and we'll store that on our object there, and we'll store it again on this one. So this now contains a rectangle for every 32 pixel wide block on our image. And then when we come to our draw animate, we effectively want to do the same as we did here. So at the position of our sprite, instead of the X and Y, we want to draw sprite.image, but we want to draw sprite.image, sorry, sprite.frame, sprite.frames, sprite.frame is the, actually let's call it sprite, let's call that frame index. So we have a frame index set to 1 initially, and that will increment as we go through, and then in our update, sprite update frame. Hang on, sorry. We also want to add a sprite time. Oh, hi Erica, welcome in. I Erica says this is witchcraft, which, to be fair, I don't think you're that far wrong. Where is the bot? Are you still asleep? It seems the bot has gone to sleep, which is helpful. Not good, night bot. Not good. This is because I turned Copilot off. Because I turned one robot off, the other one has gone out on strike. But yeah, I don't think it's like there aren't that many things, right, outside of sort of the arts, and I do consider coding an art in the same way that painting, etc., painting, drawing, and things like that are, in that it's one of the few places where something sort of comes from nowhere, right? You can create stuff out of nothing. Yeah, I do have it set up for this channel. The bot is set up for this channel. So it worked for crumbs, and then it's just decided that was it. It was going out on strike. Yeah, setting up for this channel was a bit of a pain, and I had to go through and copy most of the config from the other channel over to this one. Yeah. So yeah. But yeah, it's one of the few places we can create something. We can just bring something into existence from nothing. Is in a sort of an artistic endeavor. But so okay, so we've got our sprite update. Actually, let's call it sprite animate, which is what we're actually going to do. And so we have our frame time, and what we're going to do is we will add to that the delta time. And then if the sprite.frame time is greater than or equal to the sprite actually while the we'll use a while loop. So a while loop will just go over and over on something until the condition here is false. So we'll go while sprite dot frame time is greater than or equal to the sprite dot what do we call it, duration. Then we will take the sprite dot frame time, and we'll set that to the frame time minus the duration, and sprite dot frame index we will set to actually, does Lua support? No, it doesn't support. But so in a lot of languages, being a you can effectively just do x++, and that is the same as x equals x plus 1. So these two things would be identical in a lot of languages, but Lua is a very simple language, so it seems that it doesn't really support that one. And then if the sprite frame index is greater than or equal to the sprite you call it frames, yeah. And then I think it's to get the count, I think we do that. Is it hash frames? oh, sorry, where's it, hash sprite.frames. Okay, then we want to set sprite.frame index to 0. So this will loop through. So what we've got here is every time we call this function, we'll update. We'll call this as in our update function, and we've got our delta time, and we've got the sprite itself. Each time we take the delta time, we'll add that to the time of the animation. And then if the time we've been on that individual frame is greater than the length of that we set for each frame, we will increase the index of the frame. So which frame in our series that we're going to show to the screen. And then if the frame if that frame is greater than the total number of frames that we have, then we'll go back to 0. And because we're only incrementing by 1, then this should only ever be 1 above. So we don't need to sort of do anything clever there. And yeah, so all that's left is we need to take this and in our update function, which is here, we want to call that there, and then in the one below here we actually just used the move function. So what we'll do is we'll add a new function here, and we'll call both of those functions in that one. And then if all has gone to plan, then we should see a new, oh no, that's not working. Why is that not working? It's not working because we are still drawing regularly. So we want to draw the animate. We want to use our draw animated method instead, which will draw just a frame. So that was that one, and then we want to do the same in this one. Sorry, yeah. So I've just updated these two functions to our draw animated, and then if we restart the game again, oh, okay. So we have an error, and it was in our draw function. So we passed nil instead of a quad, which means that we tried to render a frame that was not one of the frames in the animation. So, which means that this bit here is not working. So let's put a point there, and we will run the game again. So now we're here and we have our sprite, and we can have a quick little look at the internals of the code. So we've got our frame duration is 0.5, our frame index here is 2. The frame time has a little bit left, and in our frames we have 2 values. Okay, so we can go around and see what we get on the next call. So we've still got 2 there, and now we've gone to 3. Which is if we have a look in debug console here, if we go Okay, so that's definitely, that is 2. So 3 is greater than 2, and this should get set back. Ah, this is our mistake. So we're setting it we're setting this to 0 when it should have been 1. That is me just oh, my camera is off. That is me being a bit confused because just switching between languages, because in most languages the first item in an array is item 0, because they crib from the C language and they copy what that did, whereas Lua is going back to an age before C, where basically we start counting from 1, which is how computers traditionally worked before C was a thing. And and the counting from 0 makes sense in the context of C, but doesn't make sense in any other language. They just copied C because C was the most popular one, and they wanted to sort of get some of the people that were using C to come and use their language instead. So yeah. So now if we rerun the game, and if we run it, we take without our point. So yeah, we've got a little we've got our little blob character there, and oh, that's interesting. So we're missing the bottom of the sprite, but he is moving and he is sort of animated, right? He's sort of wiggling back and forth like we wanted as we move him around. He's moving a bit slowly though, so I think we need to give him a bit of oomph. I think so. If we come in here and we've got our frame duration here, so let's try making that 0.2 seconds. So that's a fifth of a second per frame now. See if that helps caffeinate our little sorry. Yeah, so we're just changing this to 0.2 for our frame duration, and then if we run it again, here we go. It's a bit more caffeinated now. It's maybe a little bit too quick now though. A bit too caffeinated. So we went with the dark roast coffee instead of the light roast. So. Try and find someone that's a bit more cappuccino and less espresso. So yeah, this is basically like people. I know a lot of people think that sort of code is magic and arcane dark arts, but most of the time it's a case of typing some random crap into the editor, picking values. Basically you pull a value out your bot for something. You see if that works, and then if it doesn't, you go back and you sort of figure it out. Try something else, see if that works. And fiddling, and so I would say about half of the numerical values in code are pretty much picked that way. The other half you can sit down and actually maths it out a bit, but yeah. Okay, so he's moving, but he's missing his underside, which is a bit. It's not quite what we're after, right? We poor dude is missing his bottom. So I just want to have a quick check and make sure I didn't do anything stupid when we created the image. No. So he's definitely got the bottom side there. It's in the image. What have we done to lose our little dude's sort of underside? So we're going. Here we go. So we said that we told when we created the quad, we said that the original was size. It was asking for our width and height. So we gave it a width of the width and we gave it a height of the width. But the width of our image is twice the size. So okay, that's interesting. So that means it's not using this to sort of look at the it's not like using this to look at the size of the image and determine which sort of section to take out. It's using it to scale. It's using it to scale the image. So what we want to do here is we want to go for sprite, put the height in instead, and then if we give things a little run, then here we go. So he's now back to normal. To be fair, I think when we trimmed off a lot more of the height, he actually looked a little bit better. So I think when we do come to build some actual sprites and design a slime, I think we kind of want a bit more of an arch on the sprite itself. But yeah, so okay, so we've got a bit of animation there. And we can move him around, and he's animated, and he's still on top of some of the ugliest tiles known to man. But yeah, so we've got some animation. So I think at the moment we've got I think we've got a lot of the major building blocks we need for a game, right? We've got the ability to draw things onto a screen. We've got some animation. We're able to draw a map, a sort of base from some tiles. We don't have any sort of collision at the moment, but that's where things really start to get difficult and maths related. So I might try and put that off for a while. But yeah, we've got a lot of the things we need. But what we've got is we've got them in a bit of a mess. So I think it's time now that we start to tidy that up a bit. So in our source folder, let's create the actual. We're going to try and move our code into this source folder. So we'll start with a game, object. And then, actually no. We'll call it crawler, because that's sort of the name we're going with at the moment. So I think crawler is probably a good underlying sort of name for the project, outside of the branding that we'll sort of eventually land on. And then, so we're going to start to break up our code and put it into there. And how are we going to do this? I did have a couple of I did make a note, so I just want to have a look on how we could structure this. Yeah, I think, okay, so we have a crawler folder, and under that I think we'll put an engine folder for all of our engine related code, and then here we'll start defining our types. So one of the things that we've got a bunch of is these sort of X and Y positions, and what this is effectively is what most things refer to as a vector or a vector 2 or a vector 2D. So we'll go with vector 2 as a name for a module. And then we'll define our vector type here as an actual first class thing in our engine. So we'll have a concept. We'll create the concept of the vector, and then anywhere else that we use one, we'll refer to this. We'll refer back to this. So to do that, the convention in Lua from a bit of Googling is that we create a variable called m. This will be a local variable called m. And on this, we'll create a m.new function. And because it's a vector, it has an X and a Y position. So we'll give it its X and Y. And okay, so that gives us a function we can call to create our new vector. So what we'll then need to do is go local self is equal to a new table where X is equal to X and Y is equal to Y. And then we'll set the meta table of that, which is a way in Lua is a meta table contains a bunch of special overrides for within the language. So if we set that to, so by setting the meta table to M, we'll be able to inherit all of the functions that we're going to define in this module onto our new instance. And then to make that work, we go the index meta method, which is a way of giving a lookup table for anything that's not defined on our table. So on our table we have X and Y defined, but if we try and access any other value other than X and Y, it will look at what is in, it will ask this index value for that same value, for that new value that it doesn't know about, and this will either return a value for it to use or it will come back with nothing. And to do that, we can either have a table or we can have a function to look it up dynamically. And we just want the table because that will then look up within this function what we're after. So we have our, so this now gives us our thing, and what we will need to do is return M at the end. Then inside our main function here, we want to go love dot file system dot add set. So we want to set the required paths. We want to set that to love dot file system dot get the required path. So this will get the existing one. And if we look at the docs for this, so it takes the paths, that will require the function to check it. So we want a list of, we want a string that is that is separated by semicolons. And actually we'll put the way that most languages work. So what we're doing here is we're telling the language where to look for modules when we try and import them. So what we want to say is we want to look in the source for a .lua file, or we want to look in a source for whatever the past value is, and then init.lua. So these are a convention that we have. So if we let's split that onto a new line. So we're effectively saying that all of our code is in this source folder, and instead of having to require things using that source prefix, we want to look in there. But we'll also add into here the lib folder that we've defined, and this is where we'll sort of define, we'll put any extra things that we set up. So all of our code is going to be in source, or it's going to be in lib. That's where we want to include things from. And the convention here is that we'll either when we're importing, so if we try and import foo, it will look for source/foo.lua, or it will look for source/foo/init.lua. And then it will look for lib/foo.lua, then lib/foo/init.lua, and then it will move on to this default path, which will include, from memory of when I was looking at this, will be, it will then look for foo.lua, or it will look for foo/init.lua. So that just sets us up for our usage. And then what we can do is we can go local vector2 is equal to require, and what did we name this? So we have crawler/engine/vector2. So we can go crawler.engine.vector2, and yeah, because we set this path up, it sort of knows that that's where our code lives, and it knows that this is the path that we want. This is the path that we want to look. When we put these dots in, it will translate this, and it will change these dots out for a slash, and then it will try and slot that into any of these little question marks. And now that gives us our vector2 library. So now instead of here where we instantiated this, we can do vector2.new. We go 400-300, and that will create us our vector. And for the movement, we can go back to 0 and 0. Oh, hi Aaron, welcome in. Is the bot awake now? That's the question. Hey, he is. So okay, while you're awake, let's also drop some links for Splash and for Erica. Hey, here we go. Nightbot woke back up. Okay, so we've got we've used our vector class here. We can use it again here. So this was at 200 and 400. So we've now we've sort of standardized this as a concept now. So, and this was moving. Okay. No, it is a nice keyboard. It's a Apex Pro Tenkeyless. It's the most recent one they have, which I think is either the version 3 or 4. But it's quite cool. It has these weird optical switches rather than the standard sort of cherry ones. Which I used to have an older Apex Pro keyboard, one of the first generation ones, and that had a nice sound to it. But since I've updated to this one, I am very much a fan of the clackiness on this. It has a bit more of a subtle clackiness than a lot of mechanical keyboards do. Yeah. Okay. So. But yeah, it is a nice keyboard. One of the things that I get with it as well is that I can tune the activation of the key. So basically, I can set just how far down the key has to be pressed before it's registered. And it also has a feature that if I've just pressed one, it can sort of, because it's got fine-tuned information about how far a key was pressed and sort of how far it's moved. There's something in the driver which I have switched on that can detect when I'm fat fingering more than one key, because I have quite giant sausage fingers, and it's not unusual for me to mash more than one key at once. All right. So we've got, here we go. So we've got our velocity and our position vectors here. That's cool. And then we've got our position and velocity vectors here. And we're using our new vector2 class for both of these. And then when we look for where we use them, which is in our move function here. So what we're doing is we're adding these two vectors together. So we add, and to do that we add the x and the y's of both together, and we update our position by the velocity times the dt. So when we come back here, we can actually define some functions for this. So we want to go m dot 2 underscores and add self and other. So this oh no, and we don't use curly braces in Lua. We use the end keyword. So what this is, what we are doing here is when we add them together, when we use the add function, so when we do self plus other, and this is a vector2, and then this is a vector2, and one of these is a vector2 even, it will call this method, and it will pass in our two values. So we're sort of overriding how the plus works. And before that, we will actually, well, I'm going to add an extra function here, which is vector2 and what we want to do when we look at this is go return, if we get the meta table of the object, actually let's call that value because it's not really an instance method. Cool. And we should probably, actually, if we use this syntax, that's a better way of defining the methods there. So if we put a colon here, it's saying that this is a method. This method is sort of to be called on an instance, and we get an implicit self. So we want to get the meta table of the value, and we want to know if that is equal to m. So, so if our meta table, which we set here, so when we create a new vector, we set the meta table to m, and then when to test, we're going to see if it's an m. And then in here, we're going to go if m dot is vector actually I think I actually prefer the implicit self here, so we're going to go with this like this anyway. So if self, if not that, then we're going to error and go there's not a vector 2. We go if not m dot is vector 2 other, then actually let's do both of these together. So we'll go if neither of, if not that or not that, so if self is not a vector 2 or other is not a vector 2, then we send a error message saying 2 can only be added to another vector 2. Vector 2 can only be added to another vector 2, and then in here we will return a new vector, and this will be self.x plus other.x and self.y plus other.y. So now we can just add two vectors together, but what we have in our code is we have multiplication of the vectors as well. So in here, actually, I think we only need to check the secondary one. I think, well, for now, I think let's leave the error handling out, and we'll go rough for now. But we'll do this roughly for now, and then we'll come back and put some error handling in later when we have some time to test some bits and see how the error handling actually works and how things break. So, because I'm not entirely sure if this one, like, I'm wondering is that if we do sort of a plus vector, I'm not sure what self would be in that situation. Would it still be the vector and then other would be the a, or would self be a and vector be that? So I think actually we're better off, we're probably better off using a notation like this where we have the a and b values. So I think because I think that is how it will work, is that it will pass the first value to that and the second one to that, either side of the symbol. But in our multiplication, we're going to do it this way, so we'll go that by that. We'll go if if type of B is a number, then else if m dot is no, we can do this in separate ifs. I think it would be fine. So if m dot is vector 2 b, then we want to multiply the two parts of the vector together and return that. And by to and then if so we're doing our little multiplication here, and then we will have a look here, and then because this is a number, we'll just multiply both sides, which holds true with sort of how vectors work in maths. I had to recap a bunch of stuff that I haven't really looked at since I was in school for this. So that's been some of the stuff I've been looking at. But effectively, a vector has that is a bit too small. Let's let me zoom into that a bit. There we go. For some reason, the magnifier is not playing game today. Oh, hang on, wait. That's a dodge brush. That's not what I thought it was. Ah, that's what I was after, the zoom. I will learn how to use my tools eventually. But yeah, a vector is like a line from 0, 0 to another value. Where is the text? There we go. Oh. No. No, I just want normal text. So it runs from 0, 0 to some other, to effectively x and y. Yeah, it's gonna take me a little while to get used to some of these tools. I said I thought that I would have an easier time with Affinity Photo because I use the other two Affinity programs more often, like Publisher and Designer. But we need sort of pixels in this, which is where the photo one comes in. But yeah, so what we've sort of done is if we have this vector, so if we say this is sort of 2 and 4, or let's say 2 and 2, right? Let's say this is vector 2, 2. And then we add two vectors together. So we've got another vector here that is also 2, 2. So if we add those together, effectively they sort of join on like that, and we end up at 4, 4. And this is true for sort of any vector, whatever vector we use. So we can prove that by but if we had sort of 2, 2 there, and then we have another vector that is sort of yeah, let's put that there. That goes to 1, 2, and then we add those together. We sort of end up over here, which will be 3, 4 instead. Which is sort of some high school level vector maths there. And multiplying is the same, right? So if we take a vector and we times it by 2, then effectively what we end up with is a vector that's twice as long and goes to 4, 4. Or if we times it by a different number, it's going to go on each dimension. Then, like i.e. by another vector, it's gonna sort of go off in another angle. So that, and the same is true of subtraction and division as well. So we can define those in here, that we can add, we can subtract. Hi Matt, welcome in. Yeah, so we can do subtraction of the vectors by subtracting the component parts, and multiplication we can do by multiplying the component parts or by multiplying by a solid number, and the same for division. We can put a div method in here, and we can swap these times out for division. Oh, you're awake on time this week. Well, I know it's quite early for you, so so thanks for joining anyway. When I was planning this, I did have a look, and I was sort of weighing up the idea of maybe starting a couple of hours later, to make sure the time was going to be a bit nicer for people sort of further afield in time zones, but it pushed things far too close to dinner time here, so I decided in the end I'll go earlier, which sort of gets one side of the US but not the other, sort of more human hour to be awake and functional. So yeah, we have it does not like okay, no, it's just moaning about it doesn't like the compounding of the words like that, but it can live with it because this is how the standard library creates its functions, so we will follow suit. So yeah, so now we have a vector that can be multiplied and that can be divided by different values. We can come back to our move function, and instead of what we have here, we can do sprite.position equals sprite.position plus the sprite.velocity times our delta time. And we can sort of multiply our vectors together like that. We can add and multiply our vectors together like that because of these special sort of functions we defined, the meta functions, the multiplication, the subtraction, the addition, and the division ones. The language now knows how to take two of our vector items and maths them together effectively. So that's sort of simplified our code down here, and we can reuse that anywhere that we're interacting with our vectors. So we also have some logic around our vectors over here in our update function for our little player sprite. So there's one other method I want to add here. I think we'll put the meta ones near the top. Yeah, no, yeah, this is a good order. So we're going to have a split here of our module functions, then we'll have our meta functions, and then we'll have our vector functions at the bottom. And the first function I want to add is a normalized function. We will behave and we'll use American spelling, which tends to be how most people like their code spellings to work. We'll call this self. So what we're going to have is a normalize function. And this function will normalize the length of a vector to 1. And this is what we were looking at last time with the fact that we at the moment when we look at our code. So if we run our game, let's actually see if things are running. So yeah, we can see that things are still working even now that we've swapped out those values. We can still move around. But we've still got this problem here where if we are moving left and right, or we're moving up and down, we're moving at a sort of a constant speed. But when we move diagonally, we move a bit quicker. Yeah, normalize is, normalize in British English would be with a S instead of a Z, but one of the things that I guess American English has been sort of become the de facto for a lot of libraries, and it's just the way it's ended up, I guess, even with all its weirdness. So no spelling colour with a U, no S's. It's all Z's and a distinct lack of the character U. But yeah, so when we look at our movement, yeah, we still got this quicker on the diagonal than we have on the cardinal directions problem. And that is, sorry, I was showing that, but not actually. I didn't actually have the window on screen. Sorry. So yeah, we still have this. We're moving quicker on the diagonals than we are in our cardinal directions. So yeah, if we move up and down, we're going at a constant speed, near enough there. But as soon as we go diagonal, boom, off we go. Which is a common sort of bug. As I think I mentioned last week, it's like that is one you see in sort of Minecraft as well. Which means that sort of if you're ever playing Minecraft and you want to move quicker along something, if you can move diagonally, you will do. And that's down to if we sort of, I'm going to zoom in because then the fact that I can't draw a circle looks a bit better. Oh, I know, fine. All right, so if we've got you can think of the vectors of the movement of like, that's a 1. And when we do that one, that is 1 as well. But when we combine those, we get we get about 1.4 there. So what we want to do is we want to find this length, right? So we need to take the values down by the ratio of this size versus this longer length. And then we want to adjust these values the same way, which gives us this, which will give us these heights, and then we'll be able to find our 1 position here, a length of 1 here. So, so if we call this X, and this, oh no, I didn't need that, sorry, and this Y. Basic high school maths tells us that this is a right angle triangle here with a side of X and a side of Y, and this is the hypotenuse. No, that is a horrible word. That one. Hypotenuse. Hypothesis. Yeah. Well, whatever, however that's pronounced. And we know that. Let's call this Z, right? And we know that Z squared is equal to x squared plus y squared. So Z is equal to the square root of x squared plus y squared. Which means if we then take this length of 1 and we go 1 over z, and we use that for our x and our y positions, that will effectively mean that this line here, the z line, so if we go x equals x over z and y equals y over z, then out of that z will become equal to 1 rather than the 1.4 that it is now. So that's the the maths that I was almost there at, but could not actually remember the last time we streamed. So I actually spent a few minutes committing that to memory before this stream started. So what we can do here is to normalize this vector is we're going to get the ratio. Sorry, we're going to the length of the side, which will be the math dot square root of self dot x to the power of 2 plus self dot y to the power of 2. Let's put some spaces here as well so we can see this a bit better. Yeah, it took a little while to try and commit that to memory, even though it is basic high school geometry, right? But how often do we actually use a lot of the stuff we learn in high school after the tests and we're out? Every now and then it comes back, and thankfully nowadays we have the internet to look all this stuff back up on when we finally do need it. We just need to remember what to look for, right? So with our normalized, let's call it normalized. So what we're going to do is we're going to return a new vector, and this will be self.x divided by the self.x divided by our length, and self.y divided by the length. And this is a local value as well, so we want to store that. And then that should give us a normalized vector within. So no matter what the value of this is, it will give. No matter what the value of x and y are, this should then normalize it to somewhere between 0 and each of these values to somewhere between 0 and 1. That gives us a length of anywhere in that circle that we defined in that we were just looking at. So it will be anywhere around the edge of that, based on what x and y originally were. So if we, So if we define like x as 1 and y as 2, then we'll probably end up somewhere around here on the circle instead. We'll cut the circle here, and this should sort of normalize it back to the edge of the circle, I think. Put us within the bounds of this sort of radius. And yeah, so we'll end up somewhere on here, and that means that when we move around, if we use that vector for our movement, we will always be somewhere in the region of where we want. So if we go back to our movement function, here we go. So we can have a we define a new empty vector, and what we'll do is we will update this by 1. In each direction. So we still get that thing where it's going to sort of clamp the values. So if we're holding down 2 keys, it will sort of stand in opposite direction. If we tell the character to move in conflicting directions of left and right or up and down, these 2 values adding and subtracting from 0 will go from 0 to 1 to -1. Sorry, from 0 to -1 back to 1 back to 0. Or we'll go from 0 to -1 back to 0, or if only 1 key is held down, it will go to 0 or it will go to 1, which stops us from sort of favoring one input key over another. So we'll go with that. So that one will give us a vector in the right range. And what we'll do is we'll go self dot velocity is equal to our velocity vector normalized. Oh, sorry. And then actually to call a method on a table in Lua, we use a colon. So now we go that dot normalize, and that will pass our velocity to that function as the first parameter automatically for us. And then we can times that by self.speed. And now, if we run the game again, here we go. Something weird has gone on there, as we are no longer on the screen. What happened there? Let's run it again. So we don't show in the first place, which means that our position is off. Hang on. So we're moving. So this should give us a. All right. Let's inspect here and see what we're getting for our. Let's put some breakpoints in, and we'll inspect, and we'll see what we're getting for when this is running. So first up, we have a velocity of 0. We still got the new velocity is 0, and we times that by speed. If we look at our position as well, our position is where it should be. So let's skip ahead, and now we'll see that velocity is still set to not a number. Okay. So somehow okay. So because length here is 0, we divided by 0, and you cannot divide something by 0. So everything goes infinite, and therefore it doesn't know what to do. So it set it to nan, which is not a number. Abbreviation of not a number, which is a special number in programming for a non-existent number, i.e. the results of dividing something by 0, which is impossible. So we'll go if self.x is equal to 0 and self.y is equal to 0, then we will return a copy of the current one, so self.x and self.y. So this way, if we normalize a vector that is 0, we'll get 0 back. And then if we run our game again, we'll take out the breakpoints where we were pausing. Then we get our little character there, and we can move around still. Did our secondary sprite also disappear there? Let's yeah, I know, he still moves off the bottom. Okay, but yeah, so now when we're moving around, you'll notice that on the diagonals we still stay at the same speed. We don't sort of accelerate off like we were before. And if we come back to our code and we look at the velocity here, we can see that if I put a breakpoint in, okay, so no, you are not going to break where we've updated you at runtime. So let's run the game again. Here we go. So here we have our velocity is set to 0. I am moving. We'll see that we've got minus 100 there, because velocity was 1, and then when we normalized it, we got and times it by our speed of 100, we got minus 100. If we play again, yeah, and then when we try and move at the diagonal, it's now normalized that down. So instead of 100 in both directions, we've now normalized it to 70. And I will remove the breakpoint there because otherwise it will keep stopping. But that has given us our so that's given us some fine-grained control over how fast we move. And we fixed our little we fixed our movement. So we're always going to move at a constant sort of speed in all directions now, which is kind of cool. Okay, so that's tidied up our. That has tidied up our movement code quite a bit there, right? So we've got so our movement has all come down to this, and we've got no complicated maths there. We didn't have to do all of the complicated sort of maths to normalize the vector here. So for the velocity, we've just outsourced that to our function. Which, yeah, so that is pretty handy. What we might also add is I'm going to add another function here that will called normalize. And as part of that, we will return self here, and we'll update it in place. So we've got self.x is equal to self.x divided by length. self.y is equal to self.y divided by length. And then we will return self at the bottom. And then our function here actually can become a copy of the current vector, and then we call normalize on that. We'll call it with colon. So it refers to the output of this. Actually, let's make this a little bit more clear. So we'll go local. We'll make a copy of the vector, and then we'll return the normalized copy of that. We'll normalize it in place and return that copy there, and then this one will happen here. This will stop us actually creating random extra vectors when we don't need them. So we'll just have to create less. We'll have to create less things. We'll just update the things we already have and are using. So yeah, so that should be a little bit smarter. Yeah, and we've also, yeah, no, yeah, I think that's a good place for us to be with that. Okay, so next up we have some other. Let's have a look at some other bits that we have. So one of the things I was thinking about as well after the last stream is I think a lot of so try and remember my keyboard. There we go. Things to select more than one thing at once is that I want to take our map, and instead of our map being a sort of list of lists, we're just going to make it one big list of tiles, which will have a bunch of benefits for us when we come to using maps later. So now when we draw our map, how wide did we make this? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it's 16 tiles wide. So we have the, when we draw our map, we'll have a map width of 16. And we'll go for an integer value and a tile in pairs of map. So this will give us each tile sorry, not local for even. So for each tile, it will give us the integer index of it in the table. So 1, 2, 3, 4, 5, etc., and the value itself. So we're going to go. We're going to have a map width, and we're going to have a y. Actually, no, we'll just have the map width, and then for each tile, if the tile is greater than 0, then we are going to do a bit more maths here. And for our x position, we're going to the x and a percentage, which is the modulo, which is the remainder of division between I and between I and the map width. Oh, hang on, let's try and clear that. So we've got the tile set. Yeah, we'll take the modulo, which is, as I said, is the remainder of a division. So we will divide this index by 16. So 1 divided by 16 is, if we're looking at just the whole numbers, is 0 remainder 1. 17 is 1 remainder 1. 18 would be 1 remainder 2. So we get sort of a value within the range of our value. And then and then the y, we will do the math floor, and math.floor will round a value downwards. So we can take the math.floor of y divided by map width, and that will give us the y. So for 1 to 15, or 0 to, for 0 to 15, we'll get a value of actually, hang on. No, I want to do I minus 1 here instead. Instead of on the outside. And y minus 1 there instead of on the outside, yeah. So for 0, so because this is I minus 1, so for I of 1 to 16, this will we'll get a value of 0 through to 15, because we're subtracting 1, and then we're taking and we're capping it and wrapping it round every 16, and then for the y we will take the same value and we'll divide it by the map width. We'll divide it by the map width, and that map width will be that map width will be 16. So that will give us the number of times we've gone past 16 as well. So if we run the game again, hopefully, yeah. So we still get the same map rendered out, even though instead of having a big sort of grid of tiles, we've got a list. So that was one of the changes that I wanted to make, and that will come in useful in the future. The other thing we should probably look at is our tile set. So if we come back to our file system and we look in our engine, we probably want to have a tileset.lua. We'll do the same here that we did before. We have a local m. We'll return m. We'll do m dot index is equal to m there. And then we'll have a function m.new local self is equal to some table. We'll return set meta table of self to m, and we'll have a function m dot is tile set. And for that we will return the get meta table of value is equal to m. Okay, so that's our basic module set up. We just now need to work out what goes in here. So for our tile set, we're going to want an image. We'll set that later, and we're going to want a tile size. And what we'll do for our tile size is we will go local vector 2 equals require we'll require the vector 2 for that. And our tile set will be a width and a height like that. Now give us our tile size. Actually, I will be right back. I need a quick bio break, but I'll be 2 seconds. Sorry about that, and I'm back. So yeah, we've got our tile size. We're also probably going to want a margin. So we'll set that, and a spacing. And this will allow us to sort of adjust how our tile set is laid out. So if we want to go, if we want to specify that our tiles are sort of so many pixels away from the edge of the file, or if we want to put some spacing in between them so that they're less butted up together. For instance, so if we wanted to have a tile set where we had a 1 pixel border on both sides, and then a 1 pixel gap between them, and then a 32 by 32 pixel tile, we could set this up like this, and that will give us the things in the sort of structure that we were hoping for. So we can play around with our files. So, and if we put those sort of spacing in, we'll be able to look at the tiles. We'll be able to more easily see where one tile sort of starts and one ends and things like that. For now, our tiles don't have any spaces and they don't have any borders on them, so we'll have those as nothing. But we will need an image, tile size, and margin and spacing. And I guess if we use the right terminology, then this is also a texture. So this will be equal to so what we're sort of implementing here is I believe the correct term is texture atlas, which is that we have a bunch of different images all mashed together into one file. So we can set the texture atlas there, and we'll go here. We'll go tile size, or we'll default it to 32 pixels. Oh, take care, Aaron. Have a good rest. It is a Sunday afternoon, so it's a good time for one. So yeah, so if we define our new function like this, if we don't pass tile size, we'll get nil instead. And what this will do is, if by having tile size or the vector 2, if this is not nil, then we will take this value, or if it is nil, then we'll take the other value, and we'll get the defaults. So this gives us a chance to set up our table. And then the other value we want on this is the grid. So, and the grid is going to be a table. Oh, hang on. The quads even. We'll define it like that, in a way, which will make a little bit more sense in a second. But we'll also go local image width and height. Height is equal to let's, for now, love.graphics.new image, and we'll just give that we'll randomly give it a name. But what that will do is populate this. It will type this for us for now. So this now has a type. So we can go we now know what the size of the hang on, so pixel height and pixel width. Height. Okay, so we want get height. Get dimensions. Okay, so I think that, yeah. So I think those are the values we want. We'll also store these on our tile set as well. So if the image width is equal to image width, and the image height is equal to the image height is equal to image height. So these will all be fields on our returned function. So our return type. And then we want to try and calculate the value. So I might move these up out of here for now. So I think I will standardize all of these values outside of where we define self. And that means that, so when we loop over stuff, I know that after doing a bit of reading that looking stuff up in a table is a little bit expensive in terms of how the Lua language works. So by having local variables that refer to the things we're gonna have to look up often when we're looping is gonna make our CPU a bit happier. So this is why we define quads as a table here. So we'll be updating the table, but we won't have to keep looking at the quads key inside the self table. So now what we'll do is for so then we're going to loop over our image. So to work out how many tiles we have, let's go local columns, the number of columns we have of things. We will need the image width minus the margin.x minus the margin.x plus the spacing.x, because we will have because what we're going to do is we're going to divide it by the tile size.x plus the spacing.x, and what we have here, we add this extra spacing.x here because we're going to have one extra spacing in our sort of width here because we don't have a spacing after the last tile. So that will give us the number of columns that we have in the image. And we could do the same for the rows, right? We can go image dot, and we want to floor this actually. Because if the image is bigger, then we don't want any half tiles, right? So here we'll go the same. We'll go the image height minus the margin y plus the spacing.y, and we're going to divide that by the tile offset, so tile size dot y plus the spacing dot y, and then we floor that as well. Let's try and make this a bit wide at the moment. So ideally we don't want our code to be too wide because then we won't actually be able to read it easily. So we want to try so we want to try and keep our lines sort of in line with this, which is a sort of a standard in coding that every project sort of has a margin, on a right margin that we sort of try and keep everything to the side of. Okay, so we have our columns and rows there. Columns. equals columns, rows. It probably doesn't matter how many. Probably don't actually need to keep track of how many columns we have, but so then for each column, in the columns for row in the rows, we then want to go and find, we want to add our quad, so we're going to go quads dot quad.add, and that will be love.graphics.new quad, and we're going to find the x and y of each column now. So the x is going to be the column times tile size.x. So x is going to be column times no, so this is going to be 1 to 0. Oh, hang on. No, I got this wrong. So for column equals 0. Oh, hang on. I think we had an auto completion for this, didn't we? Yeah, here we go. For column is equal to 0, and we want to go up to columns, and we want to increment each time by 1. And then for row equals 1, rows, and up to rows, and we want to increment by 1 again. So it's a slightly different version of our for loop to what we had before. The other one worked on iterating over a thing, and here we have an upper bound and a lower bound, so we want to go between the two. But actually, I think what we actually want is the 0 to -1 on these. And then we're going to want to table dot insert into quads a love dot graphics dot new quad, and then given that we're going to have a x we're going to have x okay, sorry, so the first value is x, which is going to be the distance along the horizontal. So we're going to want our column, which will be 0 to the 1 less than the number of columns, 0, and that's going to be times the tile size dot x plus the tile, sorry, this spacing dot x, and then to that we're going to add the margin dot x. So this will give us a our x position, And then for the y, we're going to go row times the tile size dot y plus the spacing dot y. So for each column, we move over by the tile size and the spacing. So for our first column, and because we've gone from 0 to 1 less than the columns instead of 1 to the number of columns, our first one will be 0. So our first column will be 0 times the width and spacing, which will come to 0, and then we plus the margin. So if the margin is 1 and the tile size is 32 and the spacing is 1, then this will be 33 times 0, which will give us 0 plus 1. So we'll look at we'll look at 1 pixel in hit this way. And the same for the rows. But then when we look at column number 2, that this value will be 1. So we'll go 1 times the size plus the spacing. So in this case, if that is 32 and 1 again, that will be that will then be 33, and then we'll have the margin of 1. So that will be 1 times 33, which will be 33 plus the 1, 34, and we'll look at the 34 pixels in for our image. And then for 2, we get 33 times 2, so 66 plus the 1 for 67, and then we'll look at 67 pixels in for the third image. Oh, and that's a margin, not a marring. And then for our width and height, we have the tile size dot x and the tile size dot y, and then for our source width and source height, we have the image width, and then the image height. So, and that's upset about something. There we go, spell that correctly. So it's upset. What's that upset about? No. Oops. There we go. We closed our quad, but we didn't close the insert. And yeah, so that should be one in there and that one in there. So we create our quad, and then we insert into the quads array using table.insert, and that will give us our tile offsets. Although although part of me does wonder if instead of referring to tiles by index, do we want to refer to them by their So let's get rid of that for a sec. So we've got two ways we can refer to our tiles. So we can have like our tiles as 1, 2, 3, 4, 5, 6, 7, 8, and we can refer to them that way. Or we can refer to this one as 1, 1. Oh, sorry, wrong way around there. So then we can go 2, 1, 3 1, 4 1. Then we have then we have 1 2. Then we have 2 2. Then we have 3 2 and 4 2. And we refer to them by the coordinates. So that means that if we ever change our tile set and we decide that we're actually going to add a bunch more tiles in here, here, and here. So if we change the tiles, if we change the tile set and add more tiles, then these values stay the same, right? But then this one, if we had done that, then this would have gone through. It would have been like, okay, that's now 4, 5, 6, 7. So this becomes 8. And that goes away and that becomes 9. And that goes away and becomes 10. And that becomes 11. I think that's probably a smarter way for us to arrange our tiles. Is if we basically look at their position in the grid instead. So with that in mind, okay, let's have a little play with in Lua. In the Lua language. So this is what's called a REPL, a read execute print loop, which means we type code into here and it runs and we see and it prints the result straight out to us. So if I go like, if I type a number in, it'll be like that. If I type some maths in, we'll get the result out. If I do and I go X. Okay, so we don't get locals. Okay, that's we learn something new. If we go X, that will set the global X, and then we can reference X there. So what we want to do is we want a table. But can we set this to X equals 1, Y equals 1. So we set that, and then later on we come in and we go okay, so that didn't work. But that is going to be because it will have compared our two tables like this, and then so it will have compared our two tables, but our two tables are different tables even though the values are the same. And we haven't overridden how the equals works. So if we have where's our thing? It's source game engine vector 2.0. Is that not going to work? Oh no, sorry, it was crawler, wasn't it? Sorry, and I really can't type today. No. Let's try. Ah, hang on, I know where it was. Oh. So what we want is vector2 equals require, and then we want to tell it to look in the local folder, source dot crawler, source crawler engine vector2.lua. Are you going to work? I feel okay. I think we're gonna have to. We just have to play a bit with how. There we go. Yeah, we have to play a bit with how it transforms the paths to get what we wanted. So now we have a vector2 library here. So we can import that like that. So if we come to our vector2 library, one of the other methods we can override is function m dot eq for equals. We have a and b, and what we'll return here is return a dot x is equal to b dot x, and and a dot y is equal to b dot y. So that will give us that will override what the equal symbol does. So because if we now do this, will still be using the old code because it's in the because it's still loaded from before. So we do new 0 0. Okay, yeah, so that's still false. But then if we load this up again, and then we want to load our library in. Oh. Yeah, I couldn't actually remember last stream if Lua was Portuguese or Brazilian, but I guess this answers, right? It's copyright to I think that's a university in Rio, the University of Rio. So it turns out it is Brazilian. Yeah, okay. So yeah, so when we load our new library, because we've overridden this equals method, now when we compare two of these, it will look up the, where did we put it? Where did I put it? Here we go. That's probably not in the best spot either. Let's put it underneath the division one. Here we go. Why is this indented? Oh. Sorry, yeah, underneath the division one. Yeah. So because now it will do this comparison. So when we use the two equals, this sort of symbol maps on this operator, as it's called, which are the symbols we use in sort of maths and other things, maps onto this method instead now. And when we do it, we'll look at a and b. So we'll look at the two vectors, and we'll go, if the x's are the same and the y's are the same, then they're equal. But if they are not, if they're not the same, then they will be false. Which should then mean we can go table is equal to t is equal to an empty table. If we go t vector2 dot new 0 0 sorry, if we go t vector2 dot new let's actually go for 1 dash 1 is equal to, and then we give it a value. Then if we look up based on that vector again, we still get nil. Okay, so I'm guessing there's something else at play. So it's probably using I need to stop accidentally closing the Control C will exit things in a Linux terminal, whereas I've spent far too much time on my gaming computer recently, and my copy paste muscle memory has gone back to Control C from Windows. So okay, if I have the object, so if we have v is equal to the new vector, and we go t v is equal to some random value, then if we go look it up like that, it then works. Okay. So that is interesting. Can we do anything silly here? Like, can we go? No. Yeah, the muscle memory does get a bit weird at times. It depends how long I spend actually doing other things on the Windows computer. If I'm just using, most of the time I don't actually develop any muscle memory on there. It's only if I'm spending any sort of time in an app on there or in the web browser, which I don't tend to do as much because I tend to do most things on this computer. And then the muscle memory stays the same, and I constantly just get it wrong on Windows, which is fine. I can deal with that because I don't do it as often. But we'll go back into the work week, and by the end of tomorrow, it will be set where it needs to be. Right. So this means it's hard for us to actually specify a complex type as a key in that lookup table. So what I was hoping is that we could use our vector class. Like we do here, and we could reference our table, our tiles as like 1 1 2 1 3 1 4 1 1 2 2 2 2 3 4 2, sorry, even, and then as we could change that, we could then sort of mess around with our tile set as we like, but it's not going to be that straightforward for us. Which means that if we hard code any maps, we're going to have to re-index, and we change our tile set and we make the tile set wider than it was, but we'll have to come back to our map data, and we'll have to update the tile index of every tile to map to where that tile is now, from where that tile was to where that tile is now, if we change the size of the tile set. So that's not a huge problem for us, in that most of our maps are going to be this game are going to be auto generated. So we're going to use code to sort of figure out the map itself. So the instead of actually having a statically defined map, it will come from an algorithm instead. Except for one, potentially more than one, because we're going to also have the overworld of the game. So the dungeon itself will be auto-generated tiles, but the overworld will be individual. The overworld will be sort of static. So we're going to design like a little town, and that town will have buildings, and each of those buildings will have like a little map inside. So when you go into a building, you're sort of inside, and you can interact with some NPCs and stuff. So we will have one map, but I think we can live with it, right? We can write a little script that will update this for us and fix the map when we change the size of the tile set. But we are going to need to define the tiles and what they are and how they work. So which tiles are walls, which are grass, which ones we can walk through and can't. That we will need to have in a state that we can load. So for that, I think there is a project that tiled. This used to be the state of the art. I'm not sure if it still is. We could do a bit more research, but from memory, we'll be able to draw our maps in this. What have we got? We just want. Can we get some screenshots of how this works? Okay, so this has a. Here we go. Yeah, this is what we're after. We want to open in a new tab. There we go. So we want to have our tiles, and I think this will be able to define, and then we want to be able to draw our overworld, so we could probably use this, and then we'll load the data into our custom sets. And then for our tiles, we want to. Okay, so we're going to have the values, orientation, okay, drawing offset, and, so I think we might be able to grab the data we want from this, and I think from memory this can save our tiles and our tile set and our maps separately. So, yeah, and it can do, okay, so it can define terrains, which is how we're going to generate our maps, in that we will sort of say this area is this terrain, and so this is grass, and then this is wall, and wall will be a terrain, and then we will have algorithms to then figure out, based on those terrain types, where what tiles to draw in each. So we'll have a set of tiles. We'll have tiles defined, and let's say this tile is the border between a wall and grass. And then when a wall is next to grass in each direction, we'll look for those sort of tiles, and it will work. So I think, yeah, okay. So I think we need to manage our tile set outside of our code, and that's where we'll get our metadata from. So I think we'll probably be okay here with what we've got for our tile sets here. It's unfortunate we can't access we can't define how we're going to look things up. we can't define our lookup keys in the table as X and Y positions. We could use nested tables though. Nested tables would. We could make the grid a table of tables, but then that will make it harder for us to iterate over every grid. We could assume that we'll always have a small number of tiles, and then we can combine those two numbers into a very large number, which would also potentially allow us to store the X and Y positions. Because if we assume that no image will have more than 65,000 tiles in each direction, which seems like a reasonable assumption, because that is going to be a huge image, right? At that point, we're getting into the realms of like a 2 million pixel wide image, and we're never going to have that many tiles. We could then combine the values together, which could give us a way of defining our tiles as X and Y positions still. So I did quite like the idea of being able to update the tile set and not have to mess around too much with the images, but no, I think for now we'll keep our tile set as it is, and we'll go this way. So we've now got. Okay, so we'll go with numeric indexes for tiles. So starting at 1 and moving forward, 0 will be our no tile, and that's how we will we'll work it. Okay, so given that, we have a tile set. Instead of having our tile set here loaded as that, we will we'll import our tile set library. And we'll use I think we'll use tiles as our oh yeah. We'll use tiles as the variable that holds our tile set. We'll set that there, and then in our load function, instead of doing all of this loading here at the bottom here, we'll go tiles is equal to tileset.new. We'll pass our image in, and we'll go vector2.new, and we're going to have 32 by 32 tiles, and we won't define the width and height, and then that's it. We have our tiles set there. And then we'll add a draw method to our tile set. and this will have self, and we'll go for the index of the tile. Go for its, we'll give it an X and a Y. So, and in here we will go for our, our self dot texture, quads of, and we'll look up the index of the tile in there, and then we'll go for X and Y that we pass in, and that will draw our tile out. Actually, will that fit horizontally without wrapping? Yeah, that's nice and short, so we'll fit it all on one line. So we've got our draw method on the tiles now. So here we should be able to, for each tile in the map, if the tile is greater than 0, then we want to go tiles.draw, colon draw, and then we want the tile, and then we take the X and Y from here that we had before. Oh, oops, sorry. Oh, showing. Forgot to change back there. Thank you. Welcome in, Taurus, and thank you for letting me know. So what I did is I moved the so I added a draw function here. So we have our tile set object. I added a draw function. So we've got our self, the index of the tile, and the X and Y position to draw at. So we're going to draw the texture from our tile, and we're going to draw that. We're going to draw the quad that we defined earlier for the tile index, and we're going to draw that at the X and Y we pass. And then in here, where we were drawing our tiles manually, we're now going to go tiles, which is our tile set dot draw, colon draw, and we're going to go for the index of the tile, which is tile, and the X and Y positions, which are here. So we'll copy paste that up here, put in the brackets, and then let's make that a bit easier to look at. So that should now draw our tiles for us. And then in our load method, what I changed here, was we had a bunch of logic in here to extract the tiles from the image. So now we're just creating a new tile set in the tiles variable. We've imported our tile module here. Got our tiles there. And then we set tiles to the new tile set here, which means that the tile is now, we now have the tile set loaded, and then we can access that tiles variable, which it's now upset about because it's not recognizing this as initializing it. Yeah, but that I'll figure out how to reference, how to fix the autocomplete and stuff and make that happy later. I think we need to add some special comments that will tell it about the different types that we have, and that will get it working properly. But yeah, okay. So we've got we've got our tiles here, and we can render that. So then if we then open the game window again and we reload, oh no, index M is attempt to access index local M. So where is this? It's in tile set Lua on line 5. Ah, okay, here we go. So we didn't initialize our module as a table. So if we run that now, hey, so we've got we're now drawing our tiles, and we're drawing these straight from the tile set, which is quite, which makes it a bit nicer to work with, I think. So that's tidied that up a fair bit. And then I think for our last bit, probably the last thing we'll do today is we'll define a map.lua as well. We'll have local M is equal to that M dot index is equal to M, and return M at the bottom. And what we'll use this for is we'll define a map class. A function m.new, new, and we'll have data, a width, and a height. Width and a height, and we probably want to put the tile set. Where in the order of parameters should I put the tile set in? Let's go. Probably up front, right? So we're going to define this with a tile set. No, here we go. I think this makes sense. So when we define our tile set, our map, we're going to go, this is the data we want on the map. This is the data, these are the tiles, this is the width and height of the map, and this is the tile set we want to use to render it. So we'll go local self is equal to a new table, and we'll go the data is equal to the data height is equal to height. It's equal to the tile set. Actually, well, I think this will actually come out a bit better. So if we go and we'll define these as our vectors again. And we'll set some standards, some defaults as well. So what we'll say is tile size is equal to tile size or the tile set tile size. So this will allow us to define a map, and we can say, and we can differentiate the tile size based on the bottom, and we'll add some code to make sure that if we have sort of big tiles and a small tile set, that it sort of scales the images. But actually, for now, we will force the tile size to be the tile set tile size, and later on we'll look at extending it like that because we don't really need that for this for our initial maps. We're going to return the set meta table of this the thing. We set that to ourselves again. And in here, we're going to have a draw method. We're going to m.draw, and that is going to be it's going to take self because it's a parameter. And then for this, we will go back, if we come back to our logic for drawing the map, oh, sorry, go back to main. So we're going to have much the same, but instead of hit this, we're going to be it's going to be self.data. And we're going to have map width is equal to self map to self dot map size dot x. So take the width. We can actually close that. We don't need the files open at the moment. And then I think we'll make one last change to our tile set, and I'm going to add a function here called function m.unpack. And all we're going to do here is we're going to return self.x and self.y. So what Lua has that a lot of other languages don't have is it has multiple returns. So we can return multiple values at once from a function, and we're going to return x and y here. And what that means is that when we're in here, we can go, sorry, when we're in our map class, yeah, we can go tile width, tile height equals self dot tile size dot unpack, and that will split. That will basically set both of these values to what we want, which is not much, but it's just a little bonus for us in terms of how things it makes our code a little bit more compact, right? So this is what we're after here. So with each change that we make, we sort of tidy up the code a bit so that we make it we make things a bit more straightforward and simplified, because then what we have here though as well is we should be able to, yeah, so now what we can do now is we can go local, is we can import our map, because we now have a map type. Let's call that maps for now. So we'll have map equals nil. We'll take this data. We don't need the tiles there anymore, so we won't be using those. And then when we are loading, we can do local tiles is equal to our tile set, and local map is equal to maps.new, and then we have our data. So let's spread this over some lines a bit. So here we go. Let's indent that in. So we have our map data there. And what is this? This is the size of it. So this is a new vector 2, and I think before we worked out this was 16 across. I'm not sure how many down it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, 15, okay. I picked some funky numbers last time. So our map is 16 by 15 tiles, and we want our tiles from that we just loaded. In fact, we don't even need to assign that to a variable, right? So we could just take our tile set. Oh. We can just take our tile set and we can set it straight into the map here. All right. And then we can do table.insert objects, and our map is now, because our map implements the draw method the same as everything else, we can insert the map in there, and then we don't need anything in here at all. So this all goes away. And all we do to draw is we loop over each of the items in our objects array. And if it has a draw method, then we call it. And yeah, so now we've simplified this even further, right? So if we do the same to our sprites as well, and we give them we abstract some of this. So if we abstract like the animation into a single value, like with each step, we are slowly simplifying down the logic behind things and creating. And we sort of we take it out of the mess that we created and we put it somewhere else. And when it's somewhere else, we can structure it all nice. So in here, this is all fairly well structured. So we can see that we're setting things up, and then we're drawing. In our tile set, we can see that. Oh, I forgot the isMap function. Let me add that in quickly. m.isMap takes the value and return get meta table for value is equal to n. Yeah. So we've got our map logic is all contained in this method here. And we can document each of these functions so we know what they do and understand them. And we can do that in such a way that the VS Code can understand how they work as well. And then it will help us with filling in methods and telling us when we're doing stuff wrong. But yeah, we separated out our vector logic, so that's all in here. So that simplified down some of our stuff. We then simplified the tile set logic all out into here, so that then took that out of our main method, our main file. And now we've just moved the maps as well. So all we have left effectively is the sprite logic here, which is a bit more complicated than some of the other stuff, I'll admit. So each of these different types is probably game objects. These are effectively our game objects, and each of these will probably need a new an individual sort of thing of its own. So we'll have to define like an NPC class that takes for the NPC slime, and a player one for this one. But we can abstract away like the animation and the movement and stuff like that into like reusable behavior. And yeah, it's like it's getting a lot more. This is getting a bit more compact. One of the other things we can do though, just before we go, is if we put an init.lua here, given the way we set things up earlier, we can define a local module here that is crawler.engine.vector2 it's Lua in it. I don't think you have to show yourself out for that one, but someone was going to make that pun eventually, and if you hadn't, I might have. And then we want crawler.engine.map. So now we've got these, and then we return M from here. So this is a much simpler module than our other ones, but if we now come back to our main thread, we can local engine is equal to require crawler.engine. We had to do some messing around a bit here to deal with the fact that we didn't want to override some of. Actually, no. I think we'll leave it as is. Actually, let's get rid of that because we're not storing this reference to the map anymore, so we can call things as they are. And here we go. There we go. We will give this a different name, and then we'll store it in here with that different name. And yeah, so that we'll keep it clean, and we'll just use the locally defined reference versions. But I think what we will do is we're going to put an init.lua in this file, and we will take the stuff in our main we'll copy most of this across into here, but we will define m.draw, m.update, and m.load. These are all defined as we expected. Actually, yeah, we'll leave it. We'll define that like that, and then in our Lua code here, our main.lua, we'll go we'll clear some of this out, and in love.load we will go clear this out, and we'll go for game equals require require crawler. And then we'll go game.load. Okay. We'll make this a global variable. Oops. And then our update function will go game.update with delta time. And our draw we'll call game.draw. We probably don't need these comments here so much anymore. Yeah. So here we've got sort of our setup code. So we are enabling the debugger. We're setting up where we look for files and stuff, and then we're sort of loading the game, and then we're calling the update and draw methods on that here. And then in this file, this is now just our game logic. We're not actually using our sprite draw method. So I might actually replace our sprite draw animated with the sprite draw our sprite draw method with the new sprite draw animated, and put that back as the rendering method. Yeah. So in here, this is now pure. This is all just our game stuff. And what we're going to need is to add the module there, and then at the bottom we're going to want to return it. And then we define the m.load method, which loads up that sets up all our sprites. We've got the m.update method, which updates everything. So it loops over our array of objects and calls the update method on each of them if it defines that update method, just as we defined in our previous method. We can get rid of these comments as well. Sorry. And then we've got our draw method, our m.draw method that draws all of those objects, loops for our objects again, and draws each of them to the screen using its draw method if it should define one. We're slowly getting closer towards a sensible setup here. So when we start to abstract away the sprites and we get the sprite logic out of this load function and moved over into its own classes, or is it, well, its own types, I guess is the more correct term, because Lua doesn't really have classes, but it does use the meta tables to define types. So yeah, we'll have like a sprite type that will abstract some of this logic around position and velocity. We'll have a player type that wraps the input logic. We'll have sort of a animation type, which will define some of this animation logic. And when we've got all that put together, we're going to have very little in this sort of section here, and this is like our core game logic then. And then we'll start to abstract that out a bit more into the various parts of the game, because we're going to want to have the game's going to progress through a few different sort of scenes, right? So we're going to have the sort of title screen where it's like, okay, hi, welcome, new game, load, etc. Then we're going to have the game itself scene, and so we're going to have some of that sort of going on, and therefore what's left in here will move into those, and those will be called in this sort of root level code, and this is sort of how I see this going forward, is that we're gonna make a bit of a mess in this file, and then we'll figure out what we're doing, and then we'll sort of define some types that encapsulate what we're doing, and then we'll move the stuff over into that new class. And then each time we do that, we're gonna expand the number of types that we have in our little library of types here. We'll add functions to those types, and then they'll get richer and more functional, and we'll end up with a game that is a bit more useful. So I'll just check that the game still works, which it isn't. It's failing in Lua map on line 9. So we'll get that working quickly, and then I think we'll probably be done for the day. So what do we have here? So what was the error we had? We had that the global tile size is on line 9. That was the problem. So I was being a numpty again, and instead of using the tile set.tilesize, I had tilesize.tilesize there. So now if we run again, unpack on a nil value. Was this not tile size? So we're passing the So if we look at the tileset class, we have the tile size here. Which is set to value or that. And I am just noticing that this should probably actually be image size equals vector2 dot new width and height, just to keep it consistent that we're using the vectors for the sizes. But why is tile size not set? So we're looking at self.tilesize. Tile size is set here. So if we close things and run again, then what we have here, we have tile size is definitely set here. But when we get to the draw method, it's not set. So if we run again, so it's definitely set here, but then it crashes here because this is nil. It's not nil, it's just unpack is nil, which means that when we find our, let's move the debugger toolbar out of the way. So in our vector2 method, I definitely added an unpack, didn't I? Did I add it to the wrong? I added it to the wrong file. That is why it's not there. So then if we let's move that over into where it should be. Then if we run again, and we don't need the breakpoint there anymore. Come here, if we look at unpack, it's a function. So if we load the game window up now and continue, okay, so that is a error in our unpack method from the looks of it. No, that is an error in our code here. So instead of that, we want to go self.tilesize unpack. Give it one last run. okay, so we've got that stuff there, but our sprite is missing. Our player sprite is missing. So why is that? If we go back to our drawing function, definitely we define our sprite here, and the draw is sprite.draw. Let's try this. So we've got a sprite. Now we need to, so that's the player. It has a position. That's the other one. So is that the player again? No, that's the other sprite, I think. That's our player again, so that still has a position, and the position is still where it was. So why is it not? Why is it not showing? Is the question we have. Is the question now? If it's still there. Ah. Okay. So when we set up our objects, we we insert the values. So we're inserting the value at the end of the array, whereas I think we need to insert each of our values at the start of the array. Okay, other way around. So 0. So by inserting into the table at position 0, we're gonna, each item ends up at the beginning. And this is important because of the order of the things. So what we had before now, if we try again, okay, so now our maps disappeared. It's to do with the order of the stuff as we insert. So we inspect here in our draw method, and we run again. So we've got a nil. So there's these. So for each table, so this is our map, which doesn't have a draw method. So hang on, if we step in slightly, so object now, this is a sprite. We go around some more, and now this is the other sprite. So that has drawn our two sprites, but we're still missing one of the objects. So we step in. Our first object is, we have the sprite, which we draw? Come back round. We have nothing. Okay, this is very perplexing. Let's put an actual pause there just so we make sure we get each one. So first call is the sprite, and then we have sprite again. So we're missing one each. We're missing an item each loop. That was definitely not the case before, right? We definitely have. Sorry, this is the same dumb mistake I made earlier, in that we are inserting at item 0, and when we loop over things, we start at number 1. So we set those to number 1, and then we run, and yeah. So then we have our game window, and every time we run the game, here we go. We've got our everything's still working as it should. So we're rendering our map based on the map data. We can move our player around. We have a little NPC sprite that moves around for us. And all of that is running just by looping through the various game objects, of which we have 2 sprite objects and 1 map object, and they get rendered to the screen. And yeah, that is and happy days. We everything sort of works. So I think the next thing we will look at will be in the next stream. I think I'm going to wrap it up for today, but I think next week we will look at abstracting the animation into its own thing, and moving that out of this main .lua, and then we'll carry on with that, and we'll simplify our sprites down as well, hopefully, and get those into their own objects. But that's probably enough for today. So I will leave you all to your weekend. Have a great weekend. If you've enjoyed the stream, give the stream a like. If you want to keep up with our future endeavors in game dev and watching me make very silly Lua errors, then smash that subscribe button and tick the little notification bell, and I will hopefully see you all again on next Sunday for another Crafting Crawler stream. And for those of you that are into some gaming streams, then I will be back on my other channel. I'll be back on the Artisan channel on Wednesday with another Skyblock stream from Minecraft. So thank you all for joining, and until next time.